much for the nice introduction. Yeah, the topic of today, I would like to see on the screen actually. Can we start the presentation? Can I do it? Perfect. Thank you so much. As was already said, I'm wearing two hats at the agency, DLR Space Agency, to be very perfectly fine with the nomenclature. We need to say we are Space Agency at DLR, and I'm coming back to that a little later. So I'm wearing two hats. I'm the head of the German Space Life Sciences program, and on the other hand, I'm also the head of the delegation, the German delegation in the ESA program, where we try to monitor what ESA is doing, but we're also controlling and we're stimulating the ESA's program. We are the biggest, the major stakeholder in the ESA program, so we also need to tell ESA what to do in the program. It becomes a little clearer, hopefully, with the next couple of slides. So basically, DLR is a big research organization with more than 10,000 employees, distributed all over Germany in 55 institutes and more than 30 test facilities. And we have also offices in Brussels, in Washington, and also in Tokyo and Paris. But Space Agency is only a small part of it. Space Agency is here with about 260 employees. We are actually acting on behalf of the German federal government. So they are contracting us, they are telling us what to do, but that's not really the truth, because we are responsible for defining the German space program, and we also do the implementation of the program. And finally, we also implement all these activities, the German activities in the ESA frame, but also in an international frame via bilateral cooperations with space station partners, for example, like Canada, US, JAXA, also Japan and others. So this is a short overview of DLR Space Agency. The most interesting branches are here. This one here, this is called Directorate of Organizations and Infrastructure, where we coordinate all our EU and ESA activities. And this branch here, which is the Directorate of Applications and Science. And here we do the real work. We are funding, at least in our group here, we are funding science, German research institutes that send proposals to us for doing research in space, research on analogs and so on. Always proposals that have to do with kind of activities that need microgravity, need space conditions to come to results. We also are in charge of the hardware development that is necessary to do the research. We are also providing the flight opportunities, either from the national program, funded by the national program, or funded via ESA. And then we are also responsible for coordinating all these activities with ESA. And we also do the ESA delegation. That's my job, actually. I'm the head of the delegation, as I said already. And we also are very much involved in international coordination. That means in 2 weeks' time, we will travel to Rome, and where we meet a lot of colleagues from other agencies, space life sciences experts, and we discuss cooperative experiments that we do on the space station or bed rest studies. We also plan and organize isolation studies, also the upcoming isolation study that will start in end of 25, beginning of 26 in Cologne, actually in the ENVI Hub facility. And that's a very, very interesting facility that also NASA is using frequently to do bed rest studies, to really check what's going on in astronauts in isolation, what is happening with human subjects when they are very much isolated, or even lying in bed all the time. So what is happening with the body, we'll come back to that later. Yeah, spaceflight is always fascinating. There's a lot of technology involved, there's technique involved. It's really fascinating. But of course, it's also fascinating to have humans in the space environment. And that is really what we do. We do space life sciences. We really look into what is happening to biology, what is happening to plants, to animals, to the human body when they are put now from 1G conditions into microgravity environment, in the very extreme environment of space. There are a lot of extreme conditions. We have microgravity, almost weightlessness. or we feel it really weightless. It is not perfectly weightless, therefore we always say microgravity and not weightlessness. We have a lot of isolation, we have confinement, we have radiation, and we have the distance from Earth that makes communication a bit more difficult and so on. We come back to that later. What you can already see is that some astronauts are a bit confused when they travel in space and going into space. This is Hans Schlegel during the commissioning of the Columbus module of the ISS. And if you look a bit more closely, you see he mixed up the left and the right boot when he put it on. It's always a funny story, but when he came back, he told me, well, I haven't even noticed, not even now. And I was the first person to tell him what he did. So, and that is already indicating that a lot of things are happening in space. So when you look into the different system of the human body, you will find a lot of different things that are changed. And this is quite normal. All these kind of things that are happening with the brain, with the hormones, with the cardiovascular system, with the spine, with muscles, with the bones, with the sensory system, with the immune system, with the blood. Even the blood is changing a lot. And the famous eye problem, the space-associated neuroocular syndrome, NASA has identified as the big gap that we have not understood and which needs to be understood before we go to Moon and Mars finally on long-term missions. So all these kind of changes are very normal. It is an adaptability. It shows the adaptability of the human body. It's good. On the other hand, the body doesn't know that we want to go back to Earth. So when they reduce the mass of the bones, when they reduce the mass of the muscles, that is normal because we don't need it in microgravity. We don't need big muscles in the legs when we don't use the legs to fly around in the ISS. But then we need to go back to Earth, and then we need to have strong muscles to withstand the 1G load. And this is a problem, of course, and therefore we need a lot of countermeasures to work against these kind of changes. This is a big story, of course, we are working on, but it is also an interesting phenomenon that all these processes, or many of these processes, resemble processes that are being started when the body becomes sick. Illnesses have certain kind of similarities to these processes, and also accelerated aging processes are very similar to what we see in sick people or in older people. And here we have a chance to check all these kind of phenomena, all these kind of processes in healthy people and in an accelerated way. So that helps us a lot to understand many of these processes. So to be a bit quicker, not to lose a lot of time, I'll give you just a short overview of all these topics we are focusing on. We are looking into the fundamental and applied biology, gravitational biology, radiation, astro and exobiology. We do space omics, bioinformatics. On the biotechnology side, we did a lot of 3D protein crystallization studies on space shuttles, not anymore. NASA is still doing a bit of protein crystallization studies. We focus now more on the onboard analytics, on 3D bioprinting, on pharmacological countermeasures and sensor development to really support crew health, monitoring crew health and performance. Health research is, of course, a major topic of our group, of our team. We are looking into the integrated human physiology to start to understand the whole process, not isolated process of the immune system or muscle and bones. We really understand how that all works together in the human body. We are working on AI-assisted diagnostics and therapy. We just started a project on quantum-based diagnostics. We really look into the digitalized and personalized medicine because it's now very important to understand not what a human is experiencing in space, but what is a specific individual experiencing in space, and how is this body changing over the time in microgravity and when it comes back. As I said, crew health monitoring is also here, and exploration. Exploration is the big topic of all the agencies right now. You probably have heard that NASA started the Artemis project. We have already one mission that was unmanned. But now we are going back to the moon. We'll have some boots on the moon, also females on the moon that never happened before, and we will try to settle on the moon. that is a big challenge, and we need to understand the psychology of living on the moon, living in a close quarter, closely together. You need to understand the team that is working together in an isolated and confined environment and so on. So we really need to understand also what is really the best solution in terms of biological life support technologies. You cannot simply put a lot of food on the moon, a lot of water on the moon. It's highly expensive. We don't have this kind of capabilities right now to put everything on the moon. We need to build a greenhouse or whatever. It costs a lot of money. So we need to try to find a solution with only a small, let's say, volume of resupply that we need on the moon. Habitat technologies is another topic, and the future topic, of course, is torpor or hibernation. You probably have seen a lot of science fiction where you put them to sleep and then you wake them up when they're shortly before they arrive on the Mars. It is not really reality right now, as you probably know, but we are working on it. And there are a lot of scientists also in Germany and in Europe. They're really trying to find solutions. They're trying to understand what's going on in a hibernation bear or in a mouse or whatever. We really try to understand, is there a kind of switch in the human body that can help us here? Okay, that just gives you a short overview of what we have done already in terms of base life sciences. We have done roughly 1,100 experiments since we started with this program 50 years ago, with Apollo and others. And we have done almost 100 experiments on the ISS right now. And if you look a bit more closely, you see that on the ISS, we have more focused on the astronaut as the human subjects, more than on the general biology. When you compare it here, we have done, of course, a lot of biology, but these experiments were mostly done on shorter missions, on parabolic flights and so on, but we'll come to that in a few seconds. Protein crystallization, as I said, was a big topic in the program, but it's, as I said, no longer is, because we have found much better solutions on Earth with laser systems and so on to come up with good crystals to be analyzed. So that gives you an overview of the platforms we are using for our science teams. And of course, the ISS is the most prominent one, the best one for most of the experiments that we do in microgravity or under microgravity conditions. So my voice is still suffering from the cold last week, but it's improving, but my voice doesn't know yet. So future platforms. The ISS is the existing platform, but you all know that we will have a decommissioning of the ISS about 2030. And then we need to have commercial platforms in orbit to continue with this kind of research. It is not decided yet who will provide this kind of platforms. We have 4 candidates. We are discussing with ESA, with NASA, who is doing what, who is building what kind of platform. And of course, we are preparing also with these kind of potential space station providers, the utilization program and much more. But our working horse really is the parabolic flights. We do a lot of experiments in parabolic flights. That's only providing a couple of seconds, 22 seconds of microgravity, but we do it repeatedly, and we can do really a lot of science during these parabolic flights. And the fun part is here that the scientist himself can experience microgravity himself. He's really experiencing, because all his samples are experiencing all the time, and that helps to understand the situation very often. But we also use unmanned platforms like here sounding rockets, which we launch from S-range in the northern part of Sweden. We have drop towers in Bremen that we use, and we use, of course, unmanned capsules that fly without an astronaut in the lowest orbit for days, weeks, or even a couple of months. We have flown a lot of experiments on the Chinese capsule, the Shenzhou 8 capsule. We have flown a lot of experiments on the Russian capsules. That, of course, is no longer an option for us. But therefore, we are quite happy that we found the NUX company, the NUX capsule of the exploration company. It's a new company in Germany, also located in Italy and in France. And they come up with a new concept for a capsule that can fly unmanned around the Earth. We can do a lot of interesting studies on these unmanned capsules, but they were also selected by ESA and by us to fly the resupply missions on the European side. So they will provide a capsule that can provide all this resupply to the ISS and is frequently traveling back and forth between ISS and Earth, hopefully starting from 27, 28 on. Yeah, this is what we are doing on Earth. We provide access for our science teams to these facilities. It is, for example, a thought already that we do a lot of studies here in the NV Hub in Cologne. It's a big facility where we can control the air pressure, the air composition and everything. We do a lot of bed rest studies here. Also NASA and ESA is using it, this facility. People are here, the subjects are lying head down tilt. We're 6 degrees head down tilt. That means that the blood is moving into the head, the same effect you have in space. That is a very good, let's say, similarity to what they experience on the orbit. The same facility or similar facility we have also in France, in Udess. We have this short-arm human centrifuge. You can put humans on this centrifuge and can study what is happening to the human body above 1G. So when we accelerate them with 2G or with 3G, we can really check what is going on in hypergravity, what is going on in lower gravity level than 1G. But of course, we cannot go to 0G, therefore we have to go into space afterwards. And we use a lot of isolation facilities, like here the Concordia station. It's an Italian-French station, very high up in the Antarctic. It's 3,200 meters high. So we have hyperbaric conditions. It's pretty cold, extreme conditions, a very good analog for space. We use the NASA's facility here, NASA's Hera facility, and also the Chinese facility and the Russian facility. We no longer do, of course, for obvious reasons. And this is a brand new facility. We just celebrated the opening of this lunar facility. It's right next to the NV Hub in Cologne. It's in the same area where we simulate conditions of Moon, but I will have a couple of slides at the end of my talk, and I can give you a short introduction into this lunar facility later. We do a lot of studies together with ESA. This is a study that is ongoing right now. This is a bed rest study where we put the subjects into this head down tilt position for 60 days. Can you imagine lying in bed for 60 days and then on top of that, lying head down tilt for 60 days? That's really, really uncomfortable. And you really feel all the negative sides of to being astronauts. So there's an ongoing study that we do at the MEDES facility in France and also in Planica in Slovenia. And we have quite a lot of seven to be very precise, experiments from Germany with German PIs, German principal investigators, looking into the effects of muscle and joints, degeneration, cardiovascular deconditioning, neurocognitive performance, physical fitness in general, and so on. We're also participating in ESA's Über program. That's really difficult to pronounce. It was Über before, and then the physical colleagues decided we will also participate in this program, and they add the P. Now you cannot pronounce it anymore, but it's still the Über project for us. And also here, a lot of Germans have already participated in this program where we look into the effects of radiation, into the biological and physical effects of space radiation. And in the next couple of years, we will hopefully see the opening of this FAIR facility where we can also mix different kinds of radiations and check what is going on in the human body, what is going on in plants and animals and so on, when they are really confronted with this kind of mixture of radiation, which is more similar, which is more resembling the real solar radiation and the deep space radiation that the human body will experience during a long travel to Mars, etc. An interesting study shown here. We are looking usually into the primary effects of this radiation, but if you really want to understand what's going on Moon, then you have also to look into the secondary effects of this kind of radiation, and these secondary effects are usually much stronger, more bad than the primary effect of the radiation itself. Very interesting. I said already, we are doing a lot of experiments on Drop Tower in Bremen. It's maybe an empty tower, probably. Most likely, you would not use it because it is completely evacuated. But we can drop samples from a height of about 100 meters. We just let it fall down, providing 4.5 seconds of microgravity. But the engineers came up with a really nice idea to use a catapult to really push the samples to the top of the tower and let it fall back. And that provides a nice microgravity time of almost 10 seconds. It's really working nicely. It's highly complicated, but it works, and they're using it frequently. They're doing more than 300 drops or catapult starts per year. Another tower is shown here. It's difficult to see, but this is a guiding system that is more or less simulating this kind of catapult launch, but it's like in a lift. You are driving up and you're driving down. But this is done in a way so that the sample is more carefully accelerated and also more carefully decelerated. It's a nice tower, and you can use it many, many times per hour. But of course, the microgravity time is only very 2.5 seconds, mostly 1.2 seconds. So that's only useful for very special processes, very special things that are very quick reactions. But as you can see here, it is also good for studying very quick processes in plants. So just gives you half a minute to relax a bit and just enjoy a parabolic flights campaign. This is one parabola. We started from 1G, and now we have the liftoff. Then we have the pull-up phase. That is a pull-up phase. And then as soon as the pilot throttling down the engines, then this plane is falling back. And this is shown here. It's falling back to Earth. And as soon as the pilot is then again throttling up to avoid that the plane is crashing, this gives you another hypergravity phase. So what we have here is during pull-up, we have 1.8 G, then we have the microgravity phase, and it's falling further up and down. And then we have the deceleration phase, where we have again 1.6, 1.7 G working on your body and on your samples. As I said, we're flying 31 parabolas in 2 hours. There's no toilet on board, so it's kind of a challenge, especially for women, but you get used to it. It works. That's what we do. We train astronauts during parabolic flights campaigns. We do a lot of cell biology studies, even use a lot of microscopes to study what is directly going on in the cell. We are looking what the brain is doing, what many systems of the human body is experiencing, how the changes, what the changes are, and we can even study brain function and so on. So it's quite, as I said, a big working horse for us. We're also doing a lot for students and for the pupils. No longer, now we have to focus on students because it was a bit difficult to involve pupils. As you probably know, it is really difficult when they are not 18 years old. But this is really a very, very successful project. We started many, many years ago. The groups of students, the teams really experiencing all phases of a space project, from sending proposals, from preparing the experiments, from doing the experiments, from analyzing the data until writing papers. And we have already very nice papers from student teams that did these kinds of experiments. They can either fly balloons, only for 1 or 2 or 3 hours. This balloon is floating in the northern part of Sweden, and then is recovered. Or we use this kind of small rockets to provide at a certain altitude. It is not microgravity mission. We don't have microgravity quality here, but we have a high altitude, and students are really coming up with interesting ideas every year. And we just started the next campaign. We did the last one in October. The last balloon campaign was in March, and we are now preparing already for the next cycle in next year. Yeah, this is a sounding rocket campaign or missions that we did since about 45 years. We do this because that provides us with 6 minutes of really, really good quality microgravity time. This is such a good microgravity time that many, many scientists really want to fly rockets instead of going to ISS, because many processes are very quick. We don't need to bring them up to ISS, wait a long time for the samples to come back. Simply not necessary in sometimes. But of course, there are many experiments that need the long-term microgravity of ISS, that's for sure. That's how it works. We launch the rocket, and then we have this kind of microgravity flight without any kind of acceleration. And then we have the re-entry phase, and then we recover the payload, bring it back to the scientists, and then they can analyze the data. That's working very nicely. It's quite inexpensive compared to an ISS experiment, but of course, it is quite a lot of money. This is one example. This is an experiment that it flew in earlier this year, in March this year. And here we have a high-resolution microscope. We had a microscope on board, and we checked the calcium responses, the very fast calcium responses in the root tip, in the Arabidopsis root tip. Worked flawlessly and was a very nice experiment. And this gives you an overview of all the human physiology experiment, mostly human physiology experiments we have right now on space station. This is not a quick experiment, but usually we do a series of experiments. That means for most human physiology studies, we need not 2 or 3, but usually 6 or 12 subjects, 12 astronauts. They need to agree to do the experiments, and it's sometimes not easy because nobody likes biopsies, but astronauts are quite strong, tough guys. Usually they agree, but not all do. So what we do here is studying the muscles, studying brain, stress, immunity, neurophysiology, cardiovascular system. The cartilage is very important. Body core temperature, bones, cervical spine, and neck muscles. We have artificial intelligence on board, and we do a lot of radiation measurements and also checking for the effects on the human body. This is really an interesting experiment because we try to understand what is artificial intelligence, what can it do for us, how can it help, and what is really the best system that is beneficial for the team of a few astronauts to help them understand the technology in the techniques in the ISS, to understand when to do what to do correctly, and so on. So this is something that is for them to help them, but it's also to entertain them, to be a companion. This is also the idea, to play music for them, to talk to them, ask for, why are you tired today, or how was your day, or something, and they can discuss it in a certain way. It's not perfect, but it's improving, and it's quite successful. Now we have an experiment, it's called Ichiban, and this experiment is about communication between 2 artificial intelligence systems. One is the German Simon, and the other one is the Japanese computer, the Japanese AI system, and they can command each other, they can talk to each other, and right now they also understand each other. That's very interesting to see, and we will have the proof of concept hopefully in a couple of months. Okay, this is what's happening in space, or what you can see in space under a high resolution microscope. This is a microtubular system of a fibroblast in microgravity. This was a hardware development that we did actually to provide the scientists with the capability to really look into the cells very closely, to really understand what are the very fast responses, what is going on in terms of adaptability and the adaptation to microgravity, and so on. What are the long-term consequences of microgravity, and so on. So this was our prototype, and now we are working on a big one. This is the FLUMIA system, a high-resolution FLUMIA system based on SIM technology, structural illumination microscope system, and this is mounted on a centrifuge. Not sure if you can start it again, hopefully. Yeah. You see, the microscope is just a little element here. All the others are the EBs, the experiment blocks, where we have the samples in. So what we do is we can really look into the cells, also we can check the microtubular system, the actin system, or vacuoles, or whatever, or even check the whole cells, calcium concentrations, how the ions are exchanged, whatever. We can really look into this live, and we can then rotate the centrifuge. We can really go from 0G to 1G and check all this, what is happening between 0 and 1G. Is there a threshold for gravity sensing, and so on. So this is really a very interesting facility for the German science community, and we also will contribute this kind of facility to ESA, and we will also make it available to the European science community, and after successful commissioning, we will also provide it to our international partners for bartering. This is the future. This is what we are discussing right now with all the other agencies, and also, of course, within ESA. This is what we are doing now. We are here on the International Space Station, and this is what we want to do in the next couple of years. We have already provided to NASA the ESM, the European Service Module, that is developed in Bremen. Actually, this then shipped to the Kennedy Space Center. This made it to the Orion capsule, and it was flying around the moon 2 years ago. And the next mission will be, we'll have some 2 astronauts on board. They will go around the moon, go back, and then Artemis 3 is the mission that will bring astronauts back to the moon. And then we'll go on. We'll have a gateway around the moon, hopefully by 28, 29. And there's also one part that is European. This is a European Esprit module and the European IHAB module. It's a habitation module. Esprit is a refilling and resupply module. And then we have the bartering element for NASA, and that will help us then bring a European also back to the moon. This is the moon part, but we're also going to Mars. You probably have heard, or you might have heard about the ExoMars mission that is ongoing since a couple of years. We had some glitches, some problems landing a rover on the moon, but now we will continue and we will bring another descent module to the Mars, collect samples, and we'll try to bring samples back to Earth together with NASA. It's a very expensive project, and it is highly debated right now, and we don't know really what the future will be. In the next couple of years, NASA will decide to go on or not. As mentioned already, we had already our share in the Artemis 1 mission. We had this kind of radiation sensors on board. It's called MARE. It's called Matroshka Asteroid Radiation Experiment. And these are 2 female phantoms. Phantom pup. What is it in English? Phantoms is like a body, female body. And this was flown already on the Russian capsule, and that was now flown also on the Orion capsule. Instead of astronauts, we had these 2 phantoms here on board, and they were measuring the radiation when the capsule flown around the moon. We have more candidates to fly on Artemis 2 and Artemis 3 missions. We have, for example, the famous space patch. We'll much more hear about it in a couple of minutes. We have a measurement system that is basically measuring the muscles, the properties of a muscle, and TEMINI is basically a temperature sensor that is not measuring the temperature simply, but it's looking into the body. What is the inner core body temperature, which is quite complicated, but it really works, and we really need to understand what the changes within the human body is, and not the temperature on the skin surface. So this will be the future. And we're also preparing for the future because, as I told you already, NASA has defined some gaps, what we really need to understand before we can go to Moon and Mars. One of these major gaps is really the eye problem. And we need to understand what is going on and how can we prevent this from happening. And therefore, we have created here a network of different teams that are working from different perspectives, on different approaches on this problem. And we have here teams that are working on the retina and organoids. They're coming up with neural networks and the effects of radiation, of gravity, changing gravity levels on the neural networks. We have teams that are working on the neurophysiology aspects, on retina, diagnostics, and the microcirculation within the eyeball. We have a team that is working on the neurocognition and on the brain structures and plasticity. So we hope to come up, we have a workshop every year where we collect all these different data and the results and discussing it with NASA, and that is quite successful. Yeah, that's almost my last slide here. Oh, I'm sorry. Not much time left for my colleague. So this is basically the introduction to Professor Kulau, and he will give you much more information about the system here. The basic message here is we are trying to sell this idea to NASA. We are really trying to come up with a solution for crew health monitoring. We really need to understand the body that is changing, as I said, in microgravity, and the astronaut need to understand what is going on with his body. And therefore, we need a suite of different kinds of sensors that gives him a clear message. I'm okay, I'm in critical conditions, or please call the doctor. And that's basically the idea behind it. But you, as I said, you will hear much more about it. Quickly, a few words about the lunar facilities. We just opened up for the public and for researchers in Cologne a couple of weeks ago. It was a big celebration here with Mr. Wüst, the Minister President of North Rhine-Westphalia, a lot of ministers and so on, the head of DLR, the head of the E3P program, ESA's program, Frank de Winne, the ESA astronaut, who is now the head of the EAC, the Astronaut Training Center in Cologne, and the head of the ISS, ESA's ISS program. Basically, the idea is to simulate the moon surface, the moon lighting, and many, many other features of the moon. The idea is to train astronauts, but also give a chance to academia, so universities, and also to industry, to companies, to come and use this kind of moon analog facility for their studies. We will also have a kind of a greenhouse here. We will also try to simulate some kind of gas compositions that could be created by in situ resources utilization on the moon, and so on. Just a lot of buzzwords. Just trying to make you understand that this is really a facility that many, many entities can use in the future to really come a bit closer to preparing to live on the moon. As I said, we're trying to simulate a special kind of sun and light conditions on the moon, because we are going to the south pole of the moon, and there we have only light from close to the horizon. That gives you a very big contrast, very high black and white contrast, which is very difficult to stand. Therefore, reduced gravity, we will have a holding system so that they are not weighing 80 kilograms, but maybe only 20 or 10 kilograms. We have the regolith here, which is very similar to the normal dust we find on the moon. And we will have a lot of simulations with respect to operations and training concepts. That's it. Thank you very much.